Okay, recording in process, I guess. Good. So let's then move on. So this is just an example of what happens in SU5. So I may not have a lot of time to talk about the BSM in this course, but I will refer to it in various occasions along the way. And this group theory part is one of the places where we can talk a little bit about a few things in beyond the standard model physics. And one of them is, well, if you talk about SU5, it's unavoidable. I cannot not say something about why do we want SU5? Why do we care about SU5? It's because SU5 was something very nice. This is the a minimal grand unified theory. Okay, SU4, the Patis-Salam group, but we come to that later. Can it be also SU5 or granification or trinification as well? I will mention slightly about that. But SU5 is the most traditional grand unified theory gauge symmetry because it contains SU3 cross SU2 cross U1 in it, as you will learn as well today. And the fundamental representation is simply given by this, as in any SU1. Then the fundamental look at the indices structure. So the epsilon tensor of SU5 is these five indices one. So the Levi-Civita generalization. So you can lower, so this is a metric of SU5, let's say, you can lower so this index by applying it to a representation with 4 indices. In the same way that we have done here, so that I have just written here, this would be for SU3, this thing here. Now you do the same for SU5, and you see that you have 1, 2, 3, 4. So the Young tableau of the conjugate, so the anti-fundamental representation is this column with 4 boxes. And of course, you can convince yourself by computing the hooks. The hooks are very simple, like it's 4, 3, 2, 1. And you put here in the denominator, and the numerator is 5, 4, 3, 2. So you start in 5 because it's SU5. So you cut everything apart from a 5. So this is a 5-dimensional. So now we confirm that this is indeed a 5-dimensional representation. And it's anti-symmetric in the sense that you can build, once again, this is a symmetric, this would be a symmetric in 4 indices, but you can add this epsilon, and the anti-symmetry is coming from this thing here, this contraction of indices here. Right, so what about the adjoint? We know that the adjoint is 24-dimensional because there is this rule of n squared minus 1 in SU1. So this is 5 squared minus 1, which is 24. And to build the adjoint, you can just do a 5 times 5 bar, and this is very simple. You stack A to the right and at the bottom. Stacking at the bottom, it's a singlet because it has 5 boxes, and stacking to the right, it's this diagram that you see here. And you can compute the dimensionality of this. So you do the hooks again, you calculate the P factor. So 5 grows to 6 there, and then decreases 1 unit further down. You calculate, and it gets 24. So this is a 24-dimensional representation. Therefore, you conclude this, that 5 times 5 bar equals to 24 plus 1. So it's not 25. It's 24 plus 1. So once again, what is important here to mention is that once you define the fundamental and anti-fundamental representations, you can really you have all you need to do everything, basically, because that's why fundamental representation is also often called as the defining representation. It really defines you the everything. It's like you can think of it as acting ladder operators. So you have the fundamental representation, you act the ladders operator of the group, and you start building the other representation. It's the same when you do an angular momentum, addition of angular momentum, etc. with ladder operators, you can go from one to another, and this is a similar procedure. So, a new topic, branching rules, and this is the last topic of the group theory, and this is a very important one, because this will start, this is already like starting with the standard model in a way, like standard model and BSM at the same time here, from a pure group theoretical perspective, before we delve into the Higgs mechanism, details, and so on, which you already delved with a lot of details in the previous.
We weren't the full details.
Sorry, Marco.
That wasn't the full details.
What?
I thought we already learned the full.
We learned the full details. We just didn't learn the full details within the standard model.
Okay.
Just because in standard model of
Okay,
SU2 and so on.
Model.
Yeah, it's an abelian, but yeah, the full details are there. Here it's going to be a little bit softer. It's just with larger representations. It's
Okay.
But we are not going into the. I would just present you the things, assuming that João already knows that, and I think he knows the details, because he did a similar thing last year, and then you understand. Okay, this is coming from that. I've seen that before. So, right. So. But why? What is the importance of these branching rules? This is something that it's not often found in literature. At least you can find this in some tables of group theory of the branching and so on, but it's not easy to find this the branching of representations. And when we're talking about branching, is how can I represent SUN in terms of its subgroups? For example, SU5. How can I branch SU5 representations into SU3 cross SU2 cross U1, even with the hypercharge here? This is very important. For example, if I think that none of you is going to work on that, or at least it's grand unified theories, but it's very important there, of course. But it's also important in other contexts where you have breakings. So it's not only guts, of course. You have a new physics model which has a larger symmetry. It doesn't have to be a grand unified theory. It might just have a larger symmetry for something. You want to explain the right-handedness of. So you have. I will actually mention it. You have like SU2L, which is a group that only sees, or an interaction that only the left-handed part of fermions are sensitive to, not the right-handed parts.
No,
but
we've seen that in the example.
With the U1s. But yes, with U1s. You have seen that with U1s. Exactly. But if you want to say, okay, but what about the right-handed part of fermions? Isn't there something analogous? Okay, so let's extend the standard model with another SU2, an SU2R. And then you need to know the branching rules. Or you want to be more ambitious and explain something else and say, okay, not SU2R, but SU3R. And also SU3L and this sort of thing. So you start thinking on these terms to explain things, and it's important to be aware of these branching rules. So these SUN groups, they have in general lower rank subgroups. And the irreps of the larger group can be decomposed in terms of the irreps of the respective subgroups. And that's the goal of this section. Right. And yeah, this is what I mean. So this is really useful in extension of the standard model when you propose new forces or new interactions. So if you ever heard about the fifth force, or to explain, for example, even to explain this G-2 of the electron that you may have already heard. It was a hot topic last year. It will be a hot topic this year, and we hope for the best reasons, not to just discover that the theory was badly calculated, and that's why an anomaly is popping out.
But that G isn't the magnetic
geomagnetic ratio. Well, yes.
Doesn't QED already explains that it's almost 2?
No. Yeah, well, QED deviates a little bit from 2.
Yes, but isn't
Schwinger shown that
in agreement with?
It's far away.
Far away.
Far away from what the experiment tells you. Far away, well, at the precision level.
Okay, but it's around 2.
It's around 2.0 something, 0, and then.
But since the experiment, there have been new calculations, right, from several groups using super computers.
Yes. with lattice simulations and so on. Yeah, because the thing is that you are talking about, Marco, about this G minus 2 deviation is only QED corrections. This is what you mean. What was done by Schwinger in 90.
I think the Dirac equation says it's 2.
Dirac equation tells it's 2.
It's 2.
Classical quantum mechanics tells you it's 1.
We put 2 anyway.
Then you have spin. You go to Dirac equation. It's 2. Now you say, okay, but now I have a quantum field theory, and I have corrections. I have vacuum fluctuations. So because with Dirac equations at 3 level, it's a classical theory. Now you go beyond the classical level, go to quantum level. You start having vacuum fluctuations, only one loop, and you get a correction, a deviation from 2. 2 point, I don't have it open here. Something like that, yes. But speaking of that,
I thought there was experimentally correct.
No, no, it's not. Let me very quickly. So Dirac equation and so on. So you can have quantum effects. So I'm not going to give this talk in full details. But Schwinger, this is what you are talking about. And of course, we should define this a mu, which is G minus 2 over 2. This is to quantify the deviation from 2. And this is the measure. And with the QED, so QED gives this correction, alpha over 2 pi, which is approximately 1 over 137. And this is the calculation. The deviation from 2, it's here. Look at also his grave, Schwinger graves, it has alpha over 2 pi. So this is what Mark is talking about. So you have a loop, you have a photon. This is a QED correction, but the standard model has all of this, right? So it's not QED. You have to put the full standard model there. And so you can have QED corrections, weak interactions, strong interactions, other possibilities in strong. This is even 2 loops here, because with strong interactions only a 2 loop level. And here, but then because this is a low energy thing, so at low energy you have hadronization. This is really complicated to do when you have quarks and gluons here. Well, in this case, only quarks are here, because these cannot be gluons, these things here, because muons don't see gluons. But these calculations here, these ones that I'm pointing out here are the ones that are really, and there are a few other more.
Okay, but even that new value calculated using full standard model is wrong.
So this is the standard model value for a mu. So just note something here, 116.
Okay.
And here you see 116. 116, and then 5, blah, 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 blah. This is the precision level.
Okay.
But, okay, again, the standard model, right?
It's about the same thing.
And now in pink, you have the differences. So the one from 2004, which is this, and the current one, which measured this, which differs from the previous one only on this digits here, and then the combination, the current one, the current days one, this is the difference here, right? So then you put this in terms of sigmas, and this is prediction is here, okay, and the current experimental average is here. This is the Brookhaven measurement. This is the Fermi lab.
It's not in the error bars.
It's not. It's at 4.2 sigma.
There's another interaction.
That's where I want to lead, but that's my optimistic and everyone that really.
What about gravity?
No, gravity would not do any sizable thing here. It's very weak, and the masses of these particles are very. So this could interact via gravitational anomaly, let's say. But gravitational anomaly would, in principle, be if I'm not missing some detail. Let's put this aside. If I'm not missing some detail, I don't believe at all that there is any sizable. If there is a gravitational anomaly, it may not. In principle, the standard model is anomaly free from gravitational anomalies. This is something that there is no time to talk about, but it's also a triangle diagram, and you can stack gravitons on the vertices, and then that's computable in an easy way at the standard model level. But the thing is, this 4.2 sigma deviation either reflects a bad calculation here, and then this comes here and things agree, or, and this is what I hope it's not the case, there's another group that is a little bit more here. I think it's the BMW group, something it's called BMW, standing for W is Wuppertal. Well, I would not guess the others. I know that the one is Wuppertal. And you have this, but let's assume that these calculations are indeed, most of them agree with this. In fact, this is a world average of a group of them. They are taking very serious care of this, not to understand this. And this year in summer, there will be new results, which will improve so we will reduce these error bars, basically. And we'll also adjust the mean value of this. So this will tell us more information. And hopefully we will be in the 5 sigma, and that will be a discovery, a confirmation. Because here, this is 1 over, for at the moment, 1 over about approximately 1 400,000, sorry, 40,000 chances of being a statistical fluctuation at the moment. And if now coming to what was Marcus saying, if this is discovered, then it may mean that we have a new particle. It can be within the standard model gauge symmetry, but it can be a new force mediating these things. You can have something like, imagine a new SU2 interaction, because we're talking about SUN groups. If you have a new SU2, you'll have new things like this, but from a new SU2. So new Z bosons and things like that. Also, these ones would have those interactions, and this can play the role for the difference. Well, in fact, I have drawn here. So this is a flavor anomaly. This is another anomaly that is popping out now. Okay, this is with leptoquarks. It's a possibility with leptoquarks here. So we have this new scalar particle here. It's a particle that has color, and it behaves as a lepton and a quark simultaneously, and it's scalar. So it behaves as a Higgs, a lepton, and a quark.
But it's a composite particle.
No. In this case, it's not. It's a fundamental one.
Okay.
I can talk a little bit about leptoquarks even in the context of this group theory, even for a take-home exercise.
I thought they were like, I don't know, protons, but instead of being all quarks, having leptons in the mix.
No,
that cannot be possible.
Because this is here a leptoquark. Well, it can be possible that as a fundamental thing, as a composite thing, having those contour numbers. But in this case, no, this is a fundamental. Yeah, this is a fundamental particle that has the quantum numbers of quarks and leptons. I mean, not spin. The spin is of a scalar, of a Higgs. It's a scalar, but then it couples to leptons. It basically mediates interactions with leptons and quarks. You see, so there is a quark here and a lepton here, and this is a vertex that mediates that interaction. Okay, I'm really deviating a little bit. Not this here; it's here. For example, we may need a new force, which is the same as saying a new interaction, if you want to start explaining anomalies. It's one of the possible ways. If you find these anomalies, this will definitely require a new, or almost definitely. We should be careful in saying definitely without doubts.
Speaking about new forces, what is the group of gravity?
The gravity is not as it stands. You can think of it as the Lorentz group. Lorentz symmetry and Lorentz. So the space-time symmetries.
Different space-times have different symmetries.
Yes, of course. So that's what would define you the symmetry of gravity. It's not a gauge symmetry. There is not, as it stands these days, it's not a gauge symmetry. There is not like a group in this sense to define what's gravity. But you can have a specific extension or a specific Lorentz symmetry. You know, it is SCO31, times T, where T is the translations, so group of translations, so the Poincare group, and the SCO 31 is the Lorentz group.
I think that Lorentz group is only a group of special relativity, because
Mm-hmm.
if you're not in the vacuum, for example, if you have a black hole, if you have a stationary black hole and have a boosted black hole moving across space.
So,
Yes.
So it's only a local.
Yes. Yeah. That's what this is what I'm used to.
gravity
Yeah,
is
but
weak.
yes,
It's
that
not in the
makes
same
sense.
picture.
It's not
Yes,
in the
it's
same
defined
picture,
by the metric.
but yeah, exactly. The metric can have symmetries.
But you can
But-
boost the partial metric and you obtain a different metric for a boosted black hole. It's called the Axelberg-Sachs metric, I think. And then you can see the chocolates and other things. But that's where the DMS group appears, because you start looking for the symmetries at no infinity.
Mm-hmm. Yes, but that's of course that's
Beyond.
so the question beyond. But the question is very interesting, and the question that Marco asked is really it's very deep. And indeed, so if you want to unify gravity so if you want to have a quantum theory of gravity and so on, then yes, you can start thinking in these terms, and you can have a group. So one of the candidates is like E8 cross E8. This is in the context of string theory, of course. E8 is like it's like SUN groups, but or more like SCO. It depends. It's an exceptional, some different. So it has some different rules. Of course, the Young tableau exists for them, but it will not be following the same rules. And to go there, it's a little bit trickier. We are not going to delve into that, of course, but that is a possibility if you have these two E8s, and you may get gravity embedded in there as a fundamental thing. But of course, this requires extra dimensions. So you see there is some geometry here in our space-time, and then when you reduce the symmetry, one of the ways of breaking symmetries, it's not if you don't do it via Higgs mechanism, if you do it via compactification of extra dimensions. What happens is that you are going to start killing generators of the original extra dimensional Lorentz group, let's say. And when you do that, this will no longer commute with the let's say per se the gauge part where the standard model is. And because the generators of one will know it's going to be an incomplete, so the group will no longer commute completely with the gauge part, then it will induce a breaking without putting any Higgs mechanism, just by geometrical means. You induce a breaking in the other part. And this is the idea of string theory or bifolding compactification. It doesn't have to do necessarily with string theory. This is the idea beyond or besides this this geometrical breaking. And gravity can arise here as like a feature of the space-time, the way the space-time looks. But that's a deep question, and of course,
in string theory, those extra dimensions, the space-time itself, is it Minkowski or it can curve as well?
it's something complicated. It's more complicated. Of course, you have. It's Minkowski is what
Minkowski
you must
is 10
obtain
dimensions.
from. You must obtain Minkowski from the original, but you can have like, for example, this Calabi-Yau spaces. You can have, which is something that I don't know more than the name. What is
The name is
Calabi-Yau, but and a figure, which is something very, very fancy. But you have the orbifolds. Orbifolds, I have a better understanding of what it is. Orbifolds, basically, it's like you define like a lattice in your space-time, and you have fixed points, and you can identify. It's like you have a circle. You can collapse a circle into a line, so basically, and you can identify 2 points like a 0 and 2 pi, and so on. And you draw a line which has the length of this circle, or half, like the 0 and the pi, and basically are removing the extra dimension of going around, and you collapse this into, and you have 2 fixed points, and in these 2 fixed points you have like lower symmetries typically. So, but you are already defining your space-time in these terms.
Okay.
But I don't know more than this. But it's a deep question, and it's another interesting line of research, of course. So back here to the point of this lecture. So here I introduce you the standard model gauge symmetry as a guidance for what follows. So which is SU3 color, which the three the fundamental representation of SU3 gives you already the three colors. You have an SU2L cross U1. This is the electroweak symmetry. So here two doublets. So these have up and down components. That's why you have up and down quarks. It's because of this SU2L thing. And why U1Y? This is the hypercharge. This is not the electric charge. And this is one of the things that that is important to bear in mind, and you will see that maybe not today. But this is not the electric charge, but it's related. Sorry. Isospin is here in SU2L. This is the weak isospin. So there is the strong isospin, which is what distinguishes like a proton from a neutron. They can be part of the same, like this isospin doublet, where the upper component is proton, the lower component is neutron. But that's like a composite thing. It's another story.
So we have the strong, the weak force.
The strong and the electroweak force.
Ah, okay, it's combined. Oh, that's why it's not the charge.
Exactly. This is electroweak. So altogether, let me use another color. Here can be this one. This one. This is electroweak force, which splits down into a weak force, which is no longer a preserved gauge symmetry in a way, in the sense that the gauge balls will have mass, and then the electromagnetic one. But this is sort of a false unification because it's not a single group, but it works as a unified force. In fact, so this is a common framework. They are tied together. They have different gauge couplings, typically noted as G and G prime, and this typically noted as G3 or GC. But these two are still tied together. Okay, so but as I say, we may want to extend the standard model to explain either to explain something at the fundamental level. Why this? Why that? So why do we have right-handed? Why right-handed are singlets in terms of standard model symmetries, or because we want to have new forces to explain G-2 or other flavor anomalies that are starting to pop out. And one of the simplest extensions is, for example, pick up the standard model part, SU3 color times SU12, but say, okay, I also have an SU2R, an SU2R that will be form doublets of the right-handed parts of the standard model fermions. For example, here in SU2L, you have, let me give you, so new L, EL, or the quarks, you have like the up L and down L. But from the SU2R, you can say, okay, while in the standard model, they are separated. So here they are separated. So you have DR, you have UR, you have ER. Well, I can say in SU2R, I have doublets of these things. I will have a doublet of UR and DR. But look, something that when you start including new interactions, what's happening there? You also can do for the leptons. So ER, but look, now if it's only ER, the standard model only predicts what is here. Right. But there is something missing here that is not in the standard model, and the left-right model, this is called a left-right model with this SU2R addition. Something that it predicts, which is the right-handed neutrinos.
Which probably exists.
Which most likely exist. This is one of the strongest things because we have neutrino oscillations, and they would not oscillate if they would be massless.
Yes.
They would be collapsed in flavor states only, and we could always tell exactly the flavor of it.
Let's suppose they are really right-handed neutrinos. It doesn't follow that they must interact with something else. For example, the right-handed electron doesn't interact with...
Exactly. Because the point, yeah, but that is why you need branching rules to understand how they interact in terms of standard model.
So even we could
symmetry.
have massive neutrinos without abandoning the standard model. Just saying, well,
Yes, we can
nothing,
simply,
nothing couples with
yes,
them.
you can simply add the right-hand
Okay,
neutrinos to the
okay.
standard model. It works, but it's like adding something by hand without, that's the, like the laziest way of, or the less, of course, it solves a problem. We need them. It solves a problem, but it's something that is only adding without further explanation. And because adding simply, there is a problem, a conceptual problem with that. Only adding is that you add, and now you need to set up a mass. They need to have a mass already, the right-hand neutrinos.
Yes, right.
And you are just putting their mass by hand in the, you say this mass has to be big because this is what the active neutrino masses, they are very light, and you have the seesaw effect. The big mass suppresses the mass of the other ones. So you start putting too many things by, and now you start assuming, or you assume other couplings, some Yukawa-like couplings that are absurdly small. So you start inducing some hierarchies. So you are adding further questions. You solve one thing, but you're adding a lot of questions. And if you start adding, if you add a symmetry that is not seen in the standard model, note I'm putting this another U1x because this is needed in order to get out of these two the hypercharge. The SU2R does not give immediately hypercharge, but if you have another U1, the combination of the generators of both can give you hypercharge. But let's forget about that detail. The thing is, if you had this, and then when you break the symmetry down to hypercharge, you see that you have you get an absolute singlet of the standard model, something that does not interact with anything in the standard model, and the other things get the right quantum numbers that you want in the standard model. But you say we don't see this SU2R, so this must be broken at by some Higgs mechanism at a larger energy scale, and then you decide what is that scale, and you say, okay, this scale is motivated by the lightness of neutrino mass, and it has to be like 10 to the 10 electron volt. Gig electron volt, James. And then you have a fundamental reason to, okay, above that, there is, they are also massless because there is no breaking, there is a preserved symmetry. But then I'm breaking it at a certain scale. I'm predicting the existence of new W bosons, new Z bosons, W prime, Z prime, which can do not at that energy scale, but they can do good things to G minus 2, the Zs in particular. But this is you are adding a fundamental reason for the existence of the neutrinos. Why? Because you have an SU2 and you have a representation, and you need to fill out its representations. You will not leave this thing without anything here as an incomplete representation. That would be a little bit odd. That in that perspective, that would be better to just add right-hand neutrino alone to the standard model. If you bring new symmetries, you are bringing new stuff into the game. And in this case, you have for free your right-handed neutrino. Yes, that's good. But there are more candidates. For example, some one that I like is that you also have SU2L cross SU2R. This is more fundamental. And then you have an SU4 for color. This is called the Patti-Salam model. This is already in the realm of unification models in a way, because this is unifying. It's like leptons. They also have color. They have a fourth color, which we denote as white. Because when you break this this SU4, this SU4.
But it's not like the sum of red, green, and blue, right?
No, it's a singlet. It's like. Yeah, white, because white, let's consider it as color neutral. It's not unfortunate name. It's actually it's well, white is colorless.
Like it's the combination of all the.
But when you say that the photons are white, then we say because you have green, blue, and red. And
exactly. I don't think it's a good name.
That's too white.
No, let's see.
And you have, when you have ions, it's blue, anti-blue, you have white. So, but
Yeah,
That's
that's
different,
but
call it
no,
yellow.
no, that's exactly the same. That's exactly the same because this blue and blue they form a singlet, which is what you call white. And here I'm singling out. So look at this SU4 color. It breaks down into SU3 color times a U1. Let's not mess around with the U1 hypercharge. Let's only think about the SU4 and SU3. And then you can write these representations in the following way. You have this is a quadruplet that branches down into a triplet of SU3 with a certain hypercharge here, plus a singlet with another hypercharge here. And this is the point. So here you had red, green, blue, white, and then you separated it into a triplet and a singlet. And white is the color neutral, what we perceive as color neutral. And of course, when you have a 3 and times a 3 bar, 3 times 3 bar, you get this blue anti-blue, red anti-red, and so on. And that's what we call white. And here it's exactly because white is what we want to be the singlet. So we can, this is leptons are white in the standard model. But you don't call them white because you don't relate them with color. But if you relate them with an extended color, then yes, you say you have to say they are white if we use this nomenclature, because we are defining white as a color singlet component when you're talking about SU3. In SU4, no. In SU4, there are 4 colors. And if the world would be SU4 colored, you would have like quarks with 4 colors. So it would be a different algebra with a higher rank and so on. Not 8 Gell-Mann matrices, but 15, I guess. 4 squared is 16. So yeah, 4 squared minus 1, it would be 15. So it would be a little bit 15 gluons instead of 8 and so on. But if you then branch it down to the color, you would get the triplet, which would behave as quarks behave, and something that is a singlet, which is singling out the whites. That's the point. So you in this model you can say, okay, leptons are in fact quarks, but SU4 quarks with a 4th color that exists in a singlet state, not in combined states in nature. And then you can have grand unified theories like SU5, SU6, and so on. I will stop with these two, not going into larger ones. But for example, in SU5, you have this 5 representation, which can have, for example, D quarks here. So D red, D green, D blue. And then you can have like E nu here, EL nu L. And this can be the right-handed ones here. Or it's actually a 5 bar. So when you can break SU5 into SU3 cross SU2 cross U1. And when you do that, it's like splitting here. So you get, in fact, something that will be a triplet of SU3 and singlet plus and singlet of so this one here, plus something that will be a singlet of SU3 and a doublet of SU2, this here. So basically these first 3 indices would be SU3 indices, and these last 2 would be SU2 indices.
So when we say we want to unify the theories, we're talking about putting them in the same SU group?
Yes, basically embedding everything. So there will be some immediate consequence
So
here.
this theory, the SU5, unifies the all the standard models?
Yes, as I will.
It's a composition of.
Yes,
all
exactly. For example, the first thing of unification is you can unify matter, you can unify. So matter is not completely unified, it's only partially unified here because it's only right-handed quarks and the leptons are here. The other ones are in a 10. They are. This is something that actually is shown below. But the one of the points here is that SU3, so you have a G3 coupling, as I said, SU2 a G, and U1 a G prime coupling. But in it, and so you write a covariant derivative of this model, and you have three terms. So you know that for U1s that you have done before, with two U1s, you have two terms in covariant derivative. Here you have three terms in the current derivative. But in SU5, you only have one with one single coupling, G5. And this is in this sense that there is a unification. The force is unified, is unique. So, and then the gauge couplings, you break the symmetry, they separate in three different ones and have to evolve. But this is already a renormalization procedure, and so they have to evolve to the values that we have that we see in the standard model. And that is possible in SU5 as well as in other ones. SU5 is one of the possibilities. SU5 has other problems, like predicting proton decay and so on. But so it's no longer widely accepted grand unified theory, but it still has some possibilities there. You can forbid proton decay by other means.
And what about the SU6? What are
Yeah,
extra particles?
SU6 contains SU5 cross U1, basically. So it's it has some other a new charge and some more a bit more particles. So SU5 does not give you anything else on top of the standard model. SU6 would give you something else on top of the standard model. That's a thing. So and you can also say I have three SU3s, so color, left and right. And this is called the quantification model, something that I've been working with, where then you have like a symmetry, a Z3 symmetry that basically identifies each of these SU3s of the first three together, which makes the gauge couplings unified. Basically, you can permute this because it's three SU3s. The structure is the same. You can identify, so permute one to another, and that makes the gauge coupling unique. But you can also add a fourth, that's why quantification, one, which is a family, which can explain why we have three generations. So, and this can even be a gauge symmetry. It can be either global or gauge. If it's global, it's a bit problematic because of the number of Goldstone bosons that are not absorbed. But if it's gauged, you can have a flavor or family gauge bosons as well, these sort of things. So this is just a flavor of many possible ways of using these SUN groups, depending on what you want to do. But how does it work? How does it work? So first, let's consider the branching of SU3 into SU2 cross U1, because this is the simplest. Well, the simplest would be SU2 into U1 cross U1, but let's already start with SU3. So you can consider an embedding. And what is this embedding? It's like you say that you have the U3 matrices that have a block, a 2x2 block with this U2 matrices, and then here an identity matrix. So this U2 are the SU2 blocks, belong to SU2. It's a 2x2 matrix. And then you can also say, I have the hypercharge generator, which is given. This is something that I will always give you in exercises. I have the hypercharge generator, which is given in terms of the 8th Gell-Mann matrix, so the lambda 8. And I define the hypercharge generator in this way, with square root 3 here, just to make charges integer numbers. I could define this with over 3 or over 6. In fact, in standard model, it's over 6. But it's just a matter of normalization. It doesn't have physical consequences, as long as you are consistent with your normalization. So I tell you, so this is the hypercharge generator, 1, 1, minus 2, where the first index 1 and 2 are SU2 indices, and the third is a singlet. The third index is just a singlet of SU2, in fact. So see this YAB, this matrix here, and there should be a tilde here to be consistent just with notation. This is expressed in the fundamental representation, as we have discussed in the beginning. So we can promptly get the branching of the fundamental representation of 3. This is the one that you just do by eye here. And from this one, you do the rest. So the triplet, you can, so one of the ways of doing this is splitting this matrix. So you do this. You identify the parts that you can see here based on this embedding. Of course, this is based on this embedding here. And what you see is you have our SU3 triplet branches down into a doublet which has one hypercharged one. So you put in an index in below the index. So you put 1, which stands for this hypercharge, plus direct sum, a singlet. So this is a singlet which has hypercharge -2. So this is how easy to get the branching of the fundamental representation of SU3. So this is once again SU3 branching into SU2 representations cross U1. Where note that these first 3, it's a triplet of SU3, but now these are representations of SU2. There is no doublet of SU3, in fact. So with the branching of 3, we can obtain all the other ones. The anti-fundamental is just conjugation. So you conjugate everything. You know that 2 is self-conjugate, so you don't need to put bars, but you have to conjugate the charge, because this is like, you can think of this as a representation, a certain psi or phi or whatever with indices and so on, but it transforms according to some exponential, which has the charges, the U1 charges on top, as you are familiar now. So you have to conjugate these charges. You put -1 here, and you put 2 here. With this, you define the branching of an anti-triplet. So now we have seen above, this is something that we have done, and we will make use of that, that 3 times 3 bar is equal to 8 plus 1. And this allows one to obtain the branching of an octet. And how do we do that? So now we are going to plug the information. So a 3 times a 3 bar, you know, a 3 is a 2 times plus 1. So it was a 2 plus 1. And a 3 bar, it's a 2 plus 1, but with the opposite hypercharges. Now you start just taking the products of the things. So this with this, so it's 2, 1 times 2 minus 1. This with this, 2, 1 times 1, 2. This with this, and this with that. So you get these 4 terms. And the hypercharges are here. Now, once again, the hypercharges, so this is the product of the representations, and you know you have the exponentials, the transformation of the fields, and you know that the exponential sum. When you're talking about the same group, the exponentials, you should sum the hypercharges. So the first one becomes neutral under this U1 hypercharge, so you put zeros here. Of course, because you also know that 2 times 2 is 3 plus 1. So you're already 3 plus 1. You have done this above. That's why, and this was done above. And you sum the hypercharge. So they are neutral. This here, what is this? So 2 times 1, you know it's only 2. And you sum the hypercharges. So you get 3. And the same here. It's only 2, but you sum the hypercharges. It's -3. And the last one, these ones cancel out. And it's 1, 0. Right? So you finally get okay, you get now in total that 3 times 3 equals to 8 plus 1. And this is what you know from the SU3 calculation. And now you compare with the final result. It's 3 plus 1, so 3 plus 1 plus 2 plus 2 plus 1. You immediately identify this singlet with one of the singlets. It doesn't matter which one, in this case, because they are identical, but separate. So this with this. And you identify this octet with the remaining. You actually can 3 plus 1 plus 2 plus 3 plus 2 plus 2. It's 8. So this is how you get the branching of the octet and also of the singlet of SU3 into SU2 cross U1 irreducible representations. So an octet There are codes to do this, of course, but here you learn how to do by hand. And I will tell you what is the code that you can even use to check your results if you like. But I may ask you, I may give you the final result for you to, because it's easy to make a mistake and then you don't know that you did the mistake. So I will give you the result that you have to achieve when necessary. And you can just repeat this. For example, for the 3 times 3, which we have seen that is 6 plus 3 bar. So you do the same thing. Now 3 times 3 is 2 plus 1, 2 plus 1 with hypercharges here. You do the same procedure. And at the end, you get this 3 plus 1 plus 2 plus 2 plus 1 with the sums of the hypercharges. Then you know that the 6 branches out in this way, right? Exactly, because this is 3 times 3 is 6 plus 3 bar. And you get, yes, exactly. Let me just recall. Because the 3 bar, we know already that this branch is in this way. So out of this product, you identify 1, 2, you get here, and the 2 minus 1 you get here. So the remaining ones are the 6 ones. And you can even compute and see. So 3 plus 2 plus 1, in fact, is 6. So you get a 6, it's a triplet with a hypercharge, or this you want charge 2, doublet, and a singlet with these charges. And for any SUN, this would also work. So for example, I give you, for example, in SU5, I can give you an SU5, an embedding of SU5 with SU3 cross SU2 cross U1. So you would have this embedding here. And I give you the hypercharge matrix, which in fact is the lambda, or is the 24th, I guess, generator of, typically the one that is denoted as the 24th generator of SU5. And I give you this hypercharge, minus 2, minus 2, minus 2, 3, 3. And you identify immediately, now recall, you have these brackets, because you have one is for SU3, the other one is for SU2. And this is the triplet. You see 3 entries here corresponding to this. It's a triplet of SU3, but a singlet of SU2. The SU2 part is below there. So it's let me split this once again for a better visualization. So this gives you a triplet of SU3, singlet of SU2 with hypercharge minus 2, and a singlet of SU3, this part here, which is a doublet of SU2 with hypercharge 3. In fact, you have seen, so you have above this that I have said. So you have a triplet and a singlet. Sorry, and a doublet. So with this, once again, you define the representation. You can promptly get the anti-fundamental one just by barring it over. And you don't need a bar in 2, but you need a bar in the 3. And with these two, you can just start putting, basically computing, making the products, bearing in mind that you have 2 products here to different groups, an SU3 and an SU2, and also the hypercharges, to get, for example, these things that will be homework. Like a 10, it's not difficult. Not difficult. And if you have this guidance, you will be able to, I'm sure you'll be able to get there. So you have this 10 that branches in this way, the 15 branches in this way, the 24 branches in this way. And you can, I think I will not ask you for the 3 dots at homework. Otherwise, it would be until the end of your life doing this and not, you would never complete it. But a few of them, it's nice to get used. So, and this will serve to introduce also the structure of the standard model. I told you that a great feature of SU5, that's why we care about SU5. It's a really nice toy model. This is a little bit like having a grand unified theory course without having to talk about supersymmetry and so on, only from the symmetric point of view. This is like the crash course on grand unification in a way, this lecture. So a great feature of SU5 is that we can embed it in the standard model. Now we have the SU3 cross SU2 and U1, as we have just seen here. here with this, given this embedding, and you have the hypercharge here. And the nice thing is that the entire standard matter contents of the standard model, everything that you have in the standard model, fits inside a 5-bar plus a 10, as I said, as well as the gauge bosons fit inside a 24, the adjoint representation. And it's a matter of counting. You can count in the standard model. Let's see, 3 times 2, 6, plus 2, 6, 7, 8, 9, 10, 9, 10, 11, 11, 12, 13, 14, 15. This is only one singlet. So 5 plus 10 is the 15. It has 15 degrees of freedom. So it's not a 15, but it has 15 degrees of freedom. And then you can just start putting. So you just build what you know about the stuff. This is what we know, what we measure in nature. We have the 3, 2, the 1, 2, 3 bar 1, 3 bar 1, 1, 1, and with these observed hypercharges, now with the normalized in the standard way. But you can identify this with what you have here above in the 5 bar, for example. 3 bar 1, 2. I can tell you, divide this by 6. So 2 divided by 6 is 1/3, right? And 3 bar 1/3. What is 3 bar 1/3? 3 bar 1 1/3. This the right-handed quarks. Now you have also 1, 2. So doublet with -3/6 is -1/2. Doublet, so 1, 2, -1/2 leptons. So these two are both inside the 5 bar. Now look at the 10 here. Let me zoom out a little bit. You can see, I think so. What we have here, 3, 2, 1/6. 3, 2, 1. So it's divided by 6. Now we have to divide all hypercharges by 6. So this fits there in the 10. 3 bar 1 -2/3. 3 bar 1 and -4 divided by 6 is this 2/3, -2/3. And finally, the right-handed electron, it's 1, 1, 1, 1, 6. So it has hypercharge. So 6 divided by 6 is 1. So that's why you have 1 here. So this, and this, they fit into this 10 of SU5. This is just a matter of counting, but it's quite beautiful in the sense that it's really symmetric. And this also serves to introduce you the quantum numbers of the standard model. Of course, with this normalization here. And the bosonic sector, it's the same. So you have, what happens to the 24? Just see, you have an octet, which has 0 hypercharge. You have a triplet of SU2 with 0 hypercharge, and you have this singlet, which is the B, typically what we call the B field. So these 3 are inside the 24. And you also have the Higgs, and now this is a big problem of SU5. This is really one of the problems, because the Higgs fits inside the 5, but it's incomplete 5. So we need something else, which is a triplet, a Higgs triplet. But that's slightly problematic because that thing can mediate proton decay, and it's one of the ways of mediating proton decay.
As long as the half-life of the proton is very huge.
Yes, that's fine. But for that, and this comes to one of the problems of SU5, which is called the doublet triplet splitting problem, because Higgs is electroweak scale. It's 246 GeV. So let's just round the numbers. It's 100 GeV. But to forbid proton decay, you need the triplet to be about 10 to the 17 gigaelectron volts. And the whole 5 is as a common mass term in the original Lagrangian. So in principle, it should have the same mass, all the components, either all very heavy, and this is a problem for the Higgs that becomes unacceptably heavy, or it's still the Higgs doublet, not the Higgs boson itself, but it's very heavy. Or you bring down the triplet inside 5, and you have a colored Higgs, let's say, that can mediate baryon violating interactions, quarks transforming into leptons in such a way that you can break apart the proton. And fast. So there are ways, fancy ways of splitting these things with extra dimensions, with typically it's that with the orbifolds, like you have different charges. We talked about that in the beginning. So if you think about a better definition, a better theory of gravity, maybe you solve this. Like you have a compactification, and then say the triplet inside 5 is odd under that certain orbifold charge, while the doublet is even. What does it mean? You can think in terms of Fourier modes. Even can be with one extra dimension, it's a cosine series. The first n is 0. The sine series, the first n is 1. So it's odd, 1, 3, 5, 7, and so on. And the mass of this tower, these are the Kaluza-Klein towers, this tower of the mass is proportional to n, proportional, it's equal to n over lambda. Lambda is the scale. Sorry, this is the radius. So the mass is lambda, it's inverse of this, basically. Sorry, no, the mass has to be 0. So the mass is n over the radius. This is what I mean. Not the, and the radius is what gives you the scale, the inverse of the radius. But the mass is n over the radius of the extra dimension. So if even if it's tiny radius, which means huge mass, huge scale. So you zoom in, it means that you are increasing the energy. When you zoom in, as inside, as more inside you go into the scale, the tiniest you go, the larger you go in energy. You need more energy to produce these particles at LHC, so or other colliders. So this means that if you get to this large scale, but the even expansion has a massless component, that would be the Higgs boson candidate. And the other one, the triplet, would be as heavy as this extra dimension, the size of this extra dimension. So that's how you can separate these two components. But that's already too far from a Higgs mechanism. Right, this is only to say that SU5 was the first Gorinified theory proposed by Georgi and Glashow here in this unit of elementary particle forces. This was the PRL. This was the PRL I was meant to talk last year in our journal club, but then there was the G-2, the talk that I had shown minutes ago. Right. With this, we can have a smooth transition to the standard model itself. I think we should go through to this now. Maybe we want to have just 5 minutes to breathe. Well, 5 minutes. We don't have much time. But let's if you want to stand up and sit down, just to wake up and to
1 minute.
1 minute, yes. Let's stand up, like stretch a little bit. Well, this is all in YouTube. I've seen YouTube doing this for the rest of the eternity. Yes, so just to do this transition. Any question, anything that anyone wants to ask? So I will just check if I have any email.
Since we're not doing anything, you were talking about the Kaluza-Klein field. Isn't it possible to unify all the strong and the weak force into a with a geometric meaning? So
yes.
Being on the left part of the Einstein equation instead of being on the stress energy, being part of the metric.
That part of being in the left part of Einstein equations, I don't know what you mean about it, because I'm not that familiar with that.
For example, in Kaluza-Klein, the electromagnetism is contained in the components of the metric.
Yeah, I think so. Yes,
So
I'm not aware of those details, but yes.
Can we include these other forces as components of a space-time metric?
Yes. Well, I'm not sure if it's components of a space-time metric. What I know, what I can tell is that the geometry, the space-time geometry, can indeed give rise to this. And indeed, you can have fields localized in different branes, and that can explain different things.
Okay.
You can do those things, of course. You can do right-handed fields.
Because my dream is that everything is geometrical. No
I-
particles. Only.
That's a really nice thing. The problem is that you need to go to higher dimensions. You cannot do that in
Yes.
4 dimensions.
That's
Or
magnetism we have to
maybe
go
even
to.
lower dimensions. Some the holography principle, it's a little bit different. I don't know the details.
No, that for electromagnetism we have to go to 5 dimensions.
At least, yes. But then there are a few problems there as well.
I guess there are problems, otherwise people will be following.
Exactly. But of course, that's a hot topic still. Well, it was hotter in the past. It's a little now. It's because that relates a lot to string theory, but not only. It's something that is not easily testable. Anyway,
Okay.
since we have a little time, let's move on. Let's now delve into the standard model properly. But for that, let's
Antonio,
start.
can I ask a quick question first?
Yeah, of course.
Why does SU2 doesn't have a bar representation? And what does the bar representation means?
Right. The bar is like conjugation. And we have seen in a previous lecture that SU2 is self-conjugated, is a pseudo-real thing. I can quickly put it here. So let me see. So it's somewhere around here. I just trying to see this. No, it has to be further below. So the SU2 was here. Here you are. Okay. Okay, cognitive fundamental. Okay, there you go. So it's that. Let's see. I'm not going to repeat all these details, but what's happening is that so take R is the conjugated, like the anti-fundamental representation, the conjugated of the two. These are R star. Here, this is shown in detail that the conjugated one is related to the fundamental one by this type of transformation. And there is like a definition of a real representation. The representation RU of a group G is real if it is equivalent via unitary transformation S to the star one, with like this, as S R S minus 1 equal to this. This is the definition of a real representation. And there's another one that if RU is antisymmetric, then S is pseudo-real. Then RU is pseudo-real. Since S equal to sigma 2 in this case, so in the case of SU2, so the doublet bar is equal to sigma 2 doublet sigma 2 minus 1. And you know that sigma 2 is antisymmetric. So this is a pseudo-real. And for this reason, for SU2, 2 equals to 2 bar. So because in essence, it's a real representation. It's pseudo-real said with more accuracy. But this is not what happens in general for SUNs. But this is why we no longer put bars on 2s. In SU2s, you always put without a bar. Okay, is it clear?
Okay, it's clear.
Then you can just digest this a little bit better on your own. But that's explained there. Okay, so to start with the standard model, and this because this is going to this first part will go into the QCD or strong interactions. let's introduce just a brief reference to Yang-Mills series. Just to see what we are going to see is what happens in terms of gauge boson interactions in Yang-Mills series. So a pure Yang-Mills series would be this term only, where you have F mu nu, but with this index A, because this is now a non-abelian symmetry. So you have an A index that runs over the adjoint representation of the group. Like if it's SU2, A is equal 1 to 3. If it's SU3, A is 1 to 8. If it's SU4, it's 1 to 15. If it's SU5, it's 1 to 24. And I will stop here. But you can say, okay, let's have some other terms here. So let's also have a fermion that has a mass and, of course, a kinetic term. You can write this explicitly in terms of internal symmetry. Internal symmetry are the SUN indices. So these big A and big B's are the SUN indices. So, and here I'm not specifying which symmetry it is, but it's a multiplet. So the fundamental representation would be psi1, psi-n, and so on. So specializing to the case of SUN, now as a gauge symmetry. So the transformation under SUN is this. And there is something missing here, which is a psi here. Psi e to the I omega A x, this is local, TA. And we have A runs from 1 to n. So this is just a generalization of the U1 transformations. Typically, we also write this as nu. And the covariant derivative is generalized in this way that you see here. So it's no longer only minus IG A mu. So you have A mu A T mu A. So this has to be a contraction here. And now for, I have decided in this part, at least unless otherwise stated, to use indices up and down to use the Einstein convention summation.
Just show the summation about. Okay.
Here. Exactly. So this is with explicit indices. So the covariant derivative is a matrix, in fact. So because you have n by n, it's n by n matrix. So you have several degrees of freedom. So you need to represent in this way. And let's start with the first proposition. So I tried to do, as I said in the first lecture, to write these lectures in trying to pose some propositions which are the results to obtain instead of going directly there. So the first result that we want to obtain is this. Like the non-abelian Yang-Mills field strength tensor reads in the following way. F mu nu equals to a part that looks like in the abelian case, but then there is an extra term that is added to it, where F, A, B, and C are the structure constants. Now note, typically, particle physicists, most of them, put the indices all up or all down, as we discussed before, and as I did actually in the first examples. But there is one thing, I was thinking a little bit about this, and this indices run in the adjoint representation. And being up or down, so there is not something like in the fundamental that being up means fundamental and being down means anti-fundamental, so they have different meanings. Here, it's irrelevant whether they are up or down. And if we establish that this F with 3 indices is structure constants, we can freely move them up and down without changing the meaning. So, because there are many of you that work in gravity, I decided to adopt here, whenever possible, or whenever I'm not lazy to rewrite a few things, to have the contractions of indices. And so this is just a disclaimer for because it's not consistent with what I did. Well, I mean, notational wise, it's not consistent with what I did above, but I'm telling you, and you know, you can do this. I accept that you do this also in exercises if you prefer. If you don't prefer, I also accept it.
Well, we'll also consider that every time a lectin index is repeated, no matter the position, always some.
Yes, yeah, exactly. Precisely. Unless it's stated that, look, these are not to be sent.
Yes, okay.
Right. So to show this, this is what I said about the A, B, and C indices here, that they can be up and down. So let's start with an abelian U1 case to this demonstration, and let's compute basically the commutator of two covariant derivatives. So the point here is that so the two derivatives commute. Well, it's not the two derivatives that commute per se. So you need to think of this as an operator acting on a certain function or field phi something, and you can act. So this is like this. So you have an operator A, which is B times C, which is this B times C. And what it means when you operate this on something, it's like acting C on phi and then acting B on there. And the commutator, this is just a reminder. The commutator says that it's the same if you apply one or another first, so it's 0, and the same here. But there are a few things here in between where it's not exactly 0. But we can expand. This part here. And when you expand, because so using this, recalling this, that you first apply the first. So you first apply the A. A now is seen as an operator on phi and the derivative outside. So you can expand. You can now expand the derivative with the derivative of this times phi plus A times the derivative of this. And when you do this expansion to these terms, so to these commutators, because you get 4 terms, you do the expansion of those that look like this, and you get terms that cut. So let's cut. This one cancels out with this one, and this one cancels out with this one here. And at the end, you get this that you know very well what it is, which is your F mu nu, and you conclude this, that the nu in abelian theory, it's given by this. Now you repeat the same processes for SUN, where you have now the generators and a few other ingredients. You can, so here you need to label names, so AA and BB, because there is one term, this one, where you must distinguish between them. But here I'm relabeling them again with A because they are dummy in this operator here separately. So you expand this. This is expanded. It's the same thing as before. You get something like the previous one that you immediately know that is this, but you also get an extra term here. And this extra term, there is the commutator between two generators. This is the algebra, the SUN Lie algebra. So it gives you the structure constants times another T. And now you note just by the even permutations of A, B, and C, you can rewrite this in this way and replace back there to get this result. Now let's put minus I GTA outside. So you have minus I GTA. So the idea was to bring TC to TA so that you can put in evidence this TA. And you get this. And now by analogy, with what you know, so this my reasoning here, okay, I know this is F mu nu, sorry, here, this is F mu nu, I have minus I G Y, Y is the hypercharge generator, and you know this is a matrix, as I shown you before. You then conclude that you can write this in the same way, where you obtain the expression for the field strength tensor of a non-abelian gauge symmetry, in this case a SUN. There is an immediate corollary of this, which is a remarkable consequence with a remarkable experimental evidence. This is what Carl Sagan said. So remarkable statements require remarkable evidence. And this is a remarkable statement that has remarkable evidence. That is, vector bosons from non-abelian gauge symmetries allow cubic and quartic self-interactions, which are absent in the abelian case. So in a pure U1 theory, you don't have vertices with the 3 photons and 4 photons. That purely doesn't exist. I mean, at the level of the Lagrangian vertices, maybe you can have corrections, quantum effects that but even there, the symmetry does not allow to generate those vertices. This is completely forbidden at all levels. What you can have is interaction of like neutral particles indirectly interacting with photons, like the Higgs interacting with photons via loops with charged particles in it. But it's not the same as generating a vertex of 3 photons and 3 or 4 photons. But sorry. Yes, exactly. This also gives rise to mass, but the point here is not the mass yet. It's the point here is that you really have those interactions that you can show by taking the pure Yang-Mills theory. Now let's just focus on pure Yang-Mills theories, and this is SUN. I'm not even specializing to SU3 or SU2 or whatever. And what you get is this. Okay, let's not follow. You can follow this on your own, but there is some indices identifications here that you can you see that there are 4 terms that in fact are the same. You have a minus sign here that because of the relabeling of indices and the anti-symmetry of this F, you pick up a plus sign. And this slide seems very busy, but the bottom line is that at the end you have this. So from here at the end you get this. So some L naught, which is like just normal kinetic terms, as you have non-abelian gauge symmetries, plus something with 3 gauge bosons, this vertex with 3 gauge bosons, another one with 4 gauge bosons, that you can write in this way. So the triple vertex is also dependent on momentum. So I decide to be this one here. So indices E rho. So the indices are the indices of so A, E, and F are the indices of the adjoint indices of the symmetry, and mu, nu, lambda are the Lorentz indices. So these are vectors. So this has the dimension, the dimension of the space-time. And you also have a quartic vertex. And this is something that you don't have in a abelian gauge symmetry. Of course, the Feynman rule is not directly this. The Feynman rule is a little bit boring to extract. You need to permute these indices, and you can find in Peskin. I see there, see Peskin and Schroeder for well, the result of these Feynman rules. They also don't bother to calculate, but they say more or less how to. But you can find in the literature if you are interested in. Not only, yes, but you have the symmetry factor, but then you have also to explicitly permute indices. So you can have mu's and lambdas and going around, but you have the symmetry factor. So you have 1/3 factorial for this and 1/4 factorial for this, but you have to sum contributions where you flip indices, and there are minus signs because of the flipping of the F factors as well. So this is not immediately just putting a symmetry factor. That is the case for scalars, for example, scalar interaction, where you don't have Lorentz indices to permute around. So, and the statement here, this is the reason why in a pure electromagnetic theory, these vertices among photons don't exist, while they do in the case of strong interactions as well as weak interactions. So you can even have photons with Zs and Ws, photons with Ws, Ws with Ws, Ws with Zs. Ws couple with photon, yes. That's why Ws have charge. They have to couple to photons, and they couple like 2 Ws and a photon, double plus, double minus, and a photon. The Zs don't couple with in the triple vertex don't couple with a photon, if I'm not wrong. Yes, I don't. Yeah, they don't because they don't have charge.
Could produce two Z balls.
Yes, yes. No. That vertex does not exist. No. That is not possible because you can think triple vertex gives you like the interaction. If a particle is, you can think in this way: if a particle doesn't have a charge, electric charge, it does not have triple vertices or cubic vertices, if you prefer, with photons. But it can have quartics. You can have Z, photon, double plus, double minus.
Oh, okay.
That you can have. But only W's can form triple vertices with photons. As well as, because they have weak charge as well, they have triple vertices with Z's. W plus, double minus, Z. In fact, Z behaves like a photon,
Yes,
but with mass. It's fundamentally like a photon. So, and we can specialize the Yang-Mills theory to the case of SU3, adding quarks, and describe the theory of strong interactions. And now we don't do considerations about SU5, but we have these quantum numbers that were already introduced. So I typically when I teach this to someone that didn't have group theory, it's really, I show these tables and they get really confused. What is this 8? What is this 3 and 3 bars? Now you know what this is, and the apertures and so on. And then you just build the invariants. You just have to compute the tensor products and so on. At this level, it's quite simple. And write down, so this is the kinetic terms for quarks. And these are basically the gauge kinetic term for the gluons. And here, so this is the gluon field strength tensor, and the G with only one index, one Lorentz index is the gluon field, basically. There are 8 because A runs from 1 to 8. That's why you have 8 gluons. And the structure constants are these F's, the SU3 structure constants. I'm not going to explicitly write them here. The covariant derivative is now given in terms of this TA, and this TA is given in terms of the Gell-Mann matrices, in the same way that the TA of SU2 is given in terms of the Pauli matrices. And G3, of course, as I said, is the SU3 color gauge coupling. And the size, so if this is large, but large in the particle physics is like 1. If you go above that, you lose the perturbativity. And in fact, this G grows to 1 point something or even more at very low energies, and the strong interaction becomes non-perturbative. That's why you have confinement. That's why quarks. So when you split quarks apart, the interaction becomes stronger and stronger. This is counterintuitive. You try to split quarks apart, and you are increasing the strength of it. Exactly. And because the energy available becomes so large that out of that energy that you are creating by splitting them apart, new quarks appear and form white states. Speaking of white, like pions, so baryons or mesons, or baryons in general, hadrons in general. I mean, baryons or mesons. So hadrons, baryons is like 3 quark states, like proton and neutron. Mesons is like 2 quark states, like pions. Right, but if you approach them, it's like asymptotic freedom. Like quarks going together, it means that you are giving a lot of energy to the system. In fact, but you are making them free. The interaction becomes weaker. It gets increasingly weaker, the SU3 interaction, when you go to higher energies. That's why you can unify this under certain circumstances, of course, with the other two. The other two are weak already, but they run through the energy scale, not a lot, but the strong runs fast and meets those at some point. And that's why you can have this unification, and you can describe with SU5s and other things. Right, what about the electric interactions? So we will start with the bosonic sector. We will leave the fermion sector for next lecture. You already know what is this. These are the gauge fields. This is only bosons, the gauge field, and here, so there are no quarks and leptons here yet, because quarks are also electric particles. And you have the Higgs here, the Higgs doublet. with hypercharge minus 1/2. These are neutral, as always. So with these quantum numbers, the electronic Lagrangian can be written. This is the kinetic terms for the Higgs doublet. This is a Higgs doublet now. This is an SU2 doublet. Bear in mind that. So this is SU2, and this is a doublet. This is the scalar potential. This is the kinetic terms of the non-abelian SU2 fields, and this is the kinetic. Sorry, yes, the kinetic terms. Yes, of the Young-Mills part. This is the Young-Mills part of SU2, and this is like the electromagnetic light, but it's not electromagnetic still. It's similar in identical in how it transforms, but not the electromagnetism per se. So the covariant derivatives now need to have, apart from SU2, so these are sigma are the Pauli matrices, and apart from U1 as we know from before. Sometimes you see in the literature y/2. Myself, I wrote in my notes y/2, but the thing is that because I have introduced SU5 and the way we came up with the charges, I realized when I was writing this that I was writing these charges already like defined over 2. So typically people write 1 here. They write not typically. It depends. Some people write, some other don't. Myself, I write in different occasions in different ways. But if it's 1 here in the Higgs, you know, the hypercharge in the covariant derivative has to come y/2. The field strengths. So these are the Levi-Civita, the symbols, and the scalar potential. Here I'm not putting a combinatory factor that could be there, but that's fine. It's absorbed into lambda. And the doublet, the Higgs is now a doublet. It's no longer like a scalar as we have. I mean, it's a scalar, but it's no longer like a singlet as we have done in the previous, in everything that you've done until now. So it has two components. So, and this is complex. So it's a phi1 plus I phi2, phi3 plus I phi4. This is the way you can split it. Right. In fact, so you can write this phi as a 1, 2, 1/2. And so these green ones are the parts. So the phi is sensitive to the SU2L cross U1Y electric interactions, but it's color neutral. So it's not sensitive to the strong interaction. So when it gets VEVs, indeed the mean and whatever mess you want to do there, it will never affect the strong sector. That's why in the vacuum, in the electric vacuum, you have preserved color charge. You don't separate the colors. There are no free colors in nature. In that example that I mentioned, like SU4, of course, you need to have a certain Higgs that breaks into SU3 cross U1 that does not preserve the SU4 color, but preserves an SU3 color inside that. Now the transformation is so you have a part with the SU2 and another one with the U1 in the usual way that we've done, and we need to these are two matrices actually, one SU2 and one that from U1, but it's defined in terms of exponential, so you can write this way. And now we just follow the same steps as before. You make a shift on phi, so basically adding this V, and at the vacuum, when so all the fields vanish, you have this configuration. This is a convenient choice, just because you can have like even V1 plus IV2 no, this is 3 and 4 here. It should be 3 and 4. You can have a completely generic. You can have a completely generic vacuum here, and it will be the same, because the thing is, if you have a generic vacuum, you can apply SU2 rotations via combinations of Pauli matrices and so on, and rotate back to this, which means that this is only orientation of axis. Now, what you do, you minimize this. So basically, you apply it to the minimum, take the first derivatives, and you get the derivative with respect to phi1 gives this. With respect to phi2, phi3, and phi4, it's already 0. But in the minimum, so it's an extreme, you want to vanish also the first derivative, which allows you to eliminate one term from your Lagrangian. I think you are also familiar with that. So this is typically also known as minimization or tadpole equation. Now note the following. This is what I said. So if we could have arrived to the exact same result if you have a generic vacuum, even with complex revs. Where you have this. So instead of v squared, you have v1 squared plus v2 squared plus v3 squared plus v4 squared equals to v squared. You would arrive to this conclusion at the end. Now you take the Hessian matrix, and that's, once again, first you take the derivatives and then you apply the minimization. So replace the mu's and put all the fields in to 0 apart from apart from the shift that should be there, and you get something quite easily in this case. And the standard model is very trivial. So 2 lambda v squared, and then this is already diagonal, which means that you have 1 Higgs, and this is the actual standard model Higgs boson. Now it's not a Higgs-like boson as I introduced in the previous. No, this is the standard model, the true Higgs boson, up to some combinatorial factor that can be absorbed into this lambda, but that doesn't matter now. And 3 Goldstone bosons. And now you recall Goldstone theorem. And I wrote 10 pages about Goldstone theorem in the previous lecture, but now I resume it to 1 sentence. There is 1 massless scalar per broken generator. So if you have 3 massless scales, it means that we must have 3 broken generators. And this leads to another proposition.
So, and we remove them by gauge fixing?
Yes,
Okay.
exactly. That's exactly what we do. So the second proposition is that the electric vacuum, so when I put this proposition, is like important results. The electric vacuum spontaneously breaks the electric symmetry in this following way. SU2 cross U1 down to U1Q, where Q is the electric charge generator given by tau 3 plus Y. I'm putting here an identity matrix because these are matrices, just to recall. And now to show this. So let's consider this vacuum without loss of generality, as I mentioned. Now you recall this, you have a certain SU2 matrix, that orthogonal matrix here, that can be given in terms of like an expansion around identity, in terms of these generators and omega parameters. And so we say that the vacuum is invariant. This is exactly the same that I wrote before. I just wanted to refresh your minds and my mind as well. So we have this OIJ, a vacuum is preserved when this preserves the structure of the vacuum. So basically OIJ Vj equals to Vi, which means that this part would have to be 0. So we say that this is the condition. We know the generator, so we don't know the generic matrix, but we know the generators. And it's enough to fulfill this. So you apply a generator to your vacuum configuration, and it has to give 0. This is a matrix 0. So this is the condition for a certain TA generator to preserve the vacuum. What we have in SU2? We have 3 generations of SU2 and 1 generator of U1. So this gives you 4 generators. You know already that you have 3 broken ones because you have 3 Goldstones, right? So this means that you have 1 remaining generator, which is the electromagnetic generator of the electromagnetism. So now you can play with generators. You apply tau 1 to the vacuum, and it's not 0, it's V0. You apply tau 2, V0. You apply tau 3, 0 minus V. You apply Y, so the hypercharge. It's also not preserving the vacuum. So there is a first conclusion. None of the electric generators preserve the vacuum. This is telling you that Y is not the electromagnetic, it's not the electromagnetic theory. U1Y is not electromagnetism. This is a confusion that I often see in some students that think that's weak interactions, the electromagnetic. No, U and Y are not electromagnetic interactions, and this is shown. This is not preserved by the vacuum alone, but you can find the combination, this Q equal to tau 3 plus Y, that does preserve the vacuum, So this is how this matrix reads. And then you apply it and you get a 0. So this one preserves the vacuum. So we arrive to the second conclusion, that it is a combination of electric generators that preserves the vacuum. That is, there is a remnant U1Q symmetry in the ground state of the theory, but Q is different than Y. So U1Y is not the same as U1Q. And actually, U1Q is related to both SU2 and U1. And is given by this. And this is the proof of that proposition, that statement. You can think of this. This is just an idea in a more quantum mechanical way with the brass and with cats in this case. So you get the tau3 with this matrix, and this it defines your isospin eigenstates plus. Sorry? Sorry? Yes, yes. Okay. The thing is, you mean so which one? Well, first of all, the thing is, first of all, you have to do like you have to do the matrix product to make sure that it's really non-zero. But yes, there is one combination that it's in principle tau1 minus or plus I tau2 that can preserve, looking like it's preserving the vacuum. But what's happening is that there are two things. Then you calculate the eigenvalues of that matrix. So this one, it's clearly, so this matrix, the eigenvalues is 1 and 0. So one thing has electric charge, another one a 0 electric charge. But this matrix that you are talking about, I think tau1 plus or minus tau2, I'm not sure. It's something like 0, 1, 0, 0. And the eigenvalues are 0, 0 of this thing. You can try it yourself. So this has no, this means that it's not there are two things. First, it's not electric charge, or even if it is electric charge, this would be a completely broken vacuum, like SU2 cross U1 going to nothing, completely breaking it. And that's not what the Higgs vacuum does. The Higgs vacuum always preserves a U1. You get the Higgs with a mass, and you get, and there is no way to, in the standard model, there is not a way to run away from that.
In fact, it's already past when I have to catch up.
Okay.
Right now, I don't know if.
Okay. It's almost finishing, but we can just stay here. Let me see. Okay, then this is an entire gauge, and we can leave this for the next time. Let's finish here because we finished in this second conclusion, and we will start here next time. So just to finalize what I was saying, that combination. So we are stopping here. This is just finishing an answer to Osvaldo. So what you say is true, but that is like a completely broken scenario, and that is not what happens in the standard model, because you need to if you go only into these group theoretical aspects, yes, you can have also that option, but that's not what your vacuum chooses. Your vacuum chooses to preserve one generator, and you can compare the eigenvalues of this Q with what you obtain to the particles in the final Lagrangian, because you can identify the charges at Lagrangian level as well, and you conclude that this is the only choice that matches with the electric vacuum in the standard model. If you are in a 2 Higgs doublet model, Marco, if you want to go, please just go, and till next week. Yes. If you have a 2 Higgs doublet model, the story is different. So you can break also the electromagnetic symmetry, which is dramatic, of course. Pedro Ferreira, if you know them, calls it the panic vacuum, I guess, because he has did some analysis to the vacuum structure of 2 Higgs doublet models. And there is like an electric vacuum, a CP breaking vacuum, and a panic vacuum, which are all those vacua where you have like a breaking of electric charge as well. So that can happen because you no longer have the freedom to rotate. So you have a generic VEV, and you don't have the freedom to rotate to two aligned VEV, only to I think, if I'm not saying wrong, let's say if you put VEVs already, so one in the down component of the first doublet here. Let me go back to here to visualize. So imagine that you have two VEVs, two doublets here. You put the VEV here in the first, and you have a second one also here. You put here a V here, a V2, let's say. You cannot. This in principle works fine. It preserves the electromagnetic theory, but if you do here like V1 and V2, you cannot simultaneously rotate these two to achieve to get 0V 0V, because these are two independent fields, and then you no longer have the freedom to rotate and collapse everything in the electron. So you can have several possibilities. So you have 4 possibilities here plus 4 possibilities there. The complex VEVs typically break also this charge and parity thing, which is it's CP violation, which can be interesting. I'm not that expert in charge and parity violation, but it's a hot topic. But there is this possibility is open in those in 2x doublet models, as well as the possibility of bringing electromagnetic symmetry, which would be dramatic. Right? Okay. I think we can stop here. And we see each other Tuesday again. And I will do an effort. I am really busy, but I will do an effort to get your first example exercises with the group theory part sometime during next week for you, like 2 weeks to solve or something like that. Okay, guys. So online, any question, anything to say?
I have questions about the standard model 1 exam.
So who is talking?
Fernando.
Fernando, okay. Let's do this way, Fernando. Because I have to speak to Ilaria, but maybe you can ask and I can reply now if it's okay. Just so
I also have questions actually
okay.
about the exams. I don't if you have time. I don't know. Okay,
I may have not a lot of time, but maybe a little bit. Just also a bit tired to deep thinking at the moment. We can have another time if we see that this is taking a lot of time. But please, what exactly are your
okay, sorry to interrupt. Just I'll be going then. If
okay, please.
Okay, bye.
Bye.
Okay, so in question 1,